Okay, so in the last video, we talked about artificial transmutation, and we kind of left off with this puzzle. And I just kind of said this as a fact, I haven't shown you any evidence that this is true, but it is. You can trust me at least for this. I'm not lying to you. But if you take the mass of a helium-4 atom, let's say it has a mass of about 4.002602 U. Remember, U is the symbol for the unified atomic mass unit. That's one of our 3 units of mass that we're dealing with. Now, a helium-4 atom is basically made of 2 protons and 2 neutrons and 2 electrons. Now, I'm not going to include the mass of the electrons just because the mass of the electron is so much smaller than the mass of the proton or the neutron. And you might say, well, isn't that where the difference is coming from? Isn't it because of the electrons? No, it's actually something different, as we'll see. In fact, if you include the mass of the electrons, that would make the situation worse. All right, so let's compare this mass of the atom to the mass of 2 protons and 2 neutrons. Okay, just ignore the mass of the electrons for now. Okay, so if I take the mass of these 2 atoms, or of this atom which I gave you, and I subtract, let's say 2 times 1.008664, and then I subtract the mass of 2 protons, I get a very small number. Okay, and in fact I actually get a negative number. And what I get is negative 0.029278 U. Okay. On these type of calculations, it's always best to not round until the very, very end of the problem. And so for right now, I'm just going to write all the digits in my calculator just so you can see how small this number is. Now notice that this value is negative, meaning that 2 protons and 2 neutrons actually have more mass than the atom of helium-4 that has 2 protons and 2 neutrons. In other words, what I'm saying is if you take 2 protons and 2 neutrons, weigh them, then wrap them up inside a nucleus, you somehow lose weight in the process of turning those 4 particles into a nucleus. Okay? This is what we call mass defect. Okay? And mass defect, we give the symbol delta M. M, of course, is mass, and delta we just include because there's obviously a difference in mass here. Okay, so this is called mass defect. Mass defect. And we're going to talk about why there's a mass defect here in a little bit. Pause it there if you need to write that down. Okay, so let's move on in the notes, talk more about this mass defect. Now, again, please make sure you're taking notes as we go through these slides. As you can see from what it says on the slide, hopefully you've already read this, the mass of a nucleus is always less than the mass of its constituent particles. When I say constituent particles, that just means the particles making up that nucleus. Okay, so in other words, when you assemble a nucleus from scratch, from the individual pieces, you somehow lose mass. Now this is an example of what's called mass defect. Okay, mass defect of a nucleus is defined as the difference between the mass of the nucleus and the mass of the sum of the masses of the individual nucleons. In other words, the calculation we did on the last slide was a calculation for mass defect. Okay, so the mass defect, I think it was like 0.0293 or something really small like that, unified atomic mass units. Now, what I just showed you was that you have a mass defect for an individual nucleus. So the calculation for mass defect that we just did was for a single nucleus. When you're comparing the mass of the nucleus to the mass of its pieces. Now there's another type of mass defect, okay, that's not for a single nucleus, but you can actually have a mass defect for a nuclear reaction. Okay, and so that's what we're going to look at now. It's really important that you distinguish between those 2 different types of mass defects. Now, I haven't told you where the mass is going. Some of you might be freaking out saying, wait, mass can't disappear. I mean, mass is conserved, right? Isn't that one of those conservation laws that they teach you in school? Mass is always conserved. Well, it turns out that's not actually true. Conservation of mass is not a real conservation law. I'm sure the chemistry teachers probably don't want me to say that, but it's true. Conservation of mass is not a real conservation law in the scope of the entire universe. And so we are going to talk about why this mass defect exists here in a little bit. But for now, let's do some more calculations. So what we just did a second ago was the calculation finding the mass defect of an individual nucleus. Okay. What I want to take a look at right now, just really quickly, is the mass defect of a nuclear reaction. Okay, now before we do that, I do want to show you this picture. This is just a visualization of the same thing. This is showing you the mass defect of hydrogen 2. In other words, if you take the mass of one proton, one neutron, and one electron, and subtract the mass of the whole atom, you don't get 0. You get a very small number, and so this mass defect is very small. Notice by the way that the way we would write this mass defect is delta M, and in IB physics we don't write AMU, we write U for unified atomic mass unit. Okay, so it's a very small number, but it's not 0. Okay, so and again, this is a mass defect for an individual nucleus. You can also have the mass defect for a nuclear reaction. Pause it there if you need to take a look at that some more. Now, what does that mean, the mass defect of a nuclear reaction? Well, here's how you calculate the mass defect of a nuclear reaction. And again, I haven't told you why the mass defect is this thing, or where that mass is going, or how is this possible. We'll get to that in a little bit. But let's say we have a nuclear reaction that looks like this. We have 2 hydrogens and 2 neutrons. And if we combine those, we get helium-4. Okay, helium-4 is 2 protons and 2 neutrons. Now, we've seen that before, of course. Helium-4 has got 2 protons and 2 neutrons. And so this is basically just a nuclear reaction equation saying if you take 2 protons, and really I should maybe write P instead of H. Sometimes you see protons written as just H1 instead of P1. It's the same thing. It doesn't matter because hydrogen 1 is the same thing as 1 proton. But anyway, so this is basically a nuclear reaction saying, if you take 2 protons and 2 neutrons and put them together, you have a nucleus of helium. That's what this nuclear reaction is saying. Here's how you find the mass defect for a nuclear reaction equation. It's very simple. You find the mass on the left side, the mass of the reactants. You find the mass on the right side, the mass of the products. And you subtract the 2. And that number is the mass defect. Okay, so left side minus right side. In other words, in the majority of nuclear reaction equations, not every nuclear reaction equations, but in most nuclear reaction equations, there is more mass on the left side than on the right side. Again, I haven't told you why there's a mass defect. We'll talk about that later. But first, let's take a look at this calculation. I'm going to go to the next slide. Pause it there if you need to write this down. It's down here, but it doesn't look as nice. Okay, so this is based off of an IB question that was given in the past, where on the IB exam, they gave them this little chart that had all the different masses on it. And what you see here in this calculation is basically the same calculation we did at the beginning of this video. You take the mass of 2 protons, 2 neutrons, add them up, okay, because that's what's on the left side. That's the mass of the reactants. And then you subtract the mass of the products. Okay, now the numbers are slightly different than what we got in the first slide of this video, just because of rounding. The numbers they're using are slightly different than the numbers we were using in our calculation, but it's very close. Okay, I think we got like negative 0.029 or 29 or something like that. They get 0.3. So that's pretty close. And if you had to, you could convert that to kilograms. You could convert that to the other unit of mass we talked about, the MeV per c squared. But that's how you find the mass defect for a nuclear reaction. Okay, you take the mass of the reactant side, you subtract the mass of the product side. Now, just to show you one more example of that, okay, here is another past IB exam question. It's asking you to find the mass defect of this reaction. Here it looks like we're taking lithium-7, we're hitting it with protons, and we're producing what looks to be, helium nuclei. Okay, so to find the mass defect, we take the mass of the left side. On the left side, I have lithium-7. So I look at my chart, I find the mass of lithium-7. That is 7.0160. Look at the unit, it's unified atomic mass units. Plus the mass of a proton, which is 1.007825. And that is the mass of the reactants. And then all we have to do is subtract the mass of the products, and we have the mass defect. So here we have 2 helium-4s. Okay, so I look at my chart. Helium-4 has a mass of 4.0026. And then I get my calculator. And I type this into my calculator. When you're doing these calculations, do keep in mind that you don't want to round into the very end of the problem, because mass defects are so tiny. If you round too early, you could completely destroy your number, because it might be too small to see. Okay, so by doing this calculation, we find a mass defect of 0.018625 U, and that is our mass defect for this nuclear reaction equation. Okay, so in other words, when this nuclear reaction happens, this is what looks to be artificial transmutation, perhaps. There's more mass on the left side than the right side. Again, I haven't told you where that mass has gone to. Okay, so far we've seen calculations involving mass defect for a nucleus, and we've seen calculations involving mass defect for a nuclear reaction. Okay, and again, the vast majority of nuclear reaction equations are going to be similar to this, where you have more mass on the left side than on the right side. And if that's not the case, we'll talk about that later. Pause it there if you need to look at that. Okay, add this to your notes. This is just kind of summarizing the 2 types of mass defect that we talked about before. And so now we're going to address the question, why do we have this mass defect? How is this physically possible? Why is mass not conserved? Because you were probably always taught, like I was, mass is conserved. They teach you that in chemistry. Okay, that's one of the great conservation laws they teach you. And really, mass is not conserved in every situation. It is conserved in situations where you don't have nuclear reactions. And so I shouldn't say, conservation of mass is a complete lie. But if you look closely enough, like if you look at the situations we're looking at, mass is not conserved. Okay, so the reason for that is it turns out that there is a thing called mass energy equivalence. Okay, mass energy equivalence, if you break that down, and we know what mass is, we know what energy is, more or less. Equivalence basically means 2 things are equal. And so the concept of mass energy equivalence is basically saying that mass is just another form of energy. Okay, so we've talked about energy like kinetic energy, potential energy, chemical energy, all that stuff. It turns out that mass in itself is just another form of energy. Okay, and the way that you do calculations with mass energy equivalence uses probably one of the most famous equations in all of the history of physics. That is E equals mc squared. Okay, and we have Einstein to thank for this idea of mass energy equivalence. And this equation that basically allows us to convert mass to energy and vice versa. Now, of course, it's not that simple. But basically what this is saying is that mass is a form of energy, and if you want to calculate how much energy mass is worth, you plug it into this equation. Now, in this equation, of course, we have mass. We have E is energy in joules, typically, and then we have C, and C is the speed of light in a vacuum. That is a universal constant that is given to you in the IB data booklet for physics. The value of C is approximately 3 times 10 to the power 8 meters per second. We've probably seen that before in 7.1. Okay, that's a number you should be familiar with. And so what this equation is saying is, if you had a way to convert mass to energy, let's say you've got 1 kilogram of mass and you convert it completely to energy. If you plug 1 into this equation and multiply by this giant number squared, you would get an enormous amount of energy. 3 times 10 to the power 8 squared, that's 9 to the power 16. Okay, you're talking about trillions of joules of energy, okay, just by converting 1 kilogram of mass to pure energy. Okay, so the answer to where did the missing mass go? Well, it got turned into energy, okay, because of mass energy equivalence. So the conservation of mass is not a true conservation law. It's only true in certain situations. The true conservation law is the conservation of energy. We talked about the conservation of energy in past units. Energy is always conserved. Okay, mass is not always conserved, but because mass is a type of energy, it fits in with the concept of energy conservation. Okay, so mass is only conserved if you don't have a nuclear reaction, but energy is always conserved. Okay, just because mass is a form of energy. All right, pause there if you need to add that to your notes. Make sure you have that equation down. This is basically, the calculation we talked about before. If you took 1 kilogram of, any type of mass and converted it to pure energy, how much energy would that be worth? Well, if you just plug in, 1 kilogram for mass and c squared, you get that number I said before, 9 times 10 to the 16 joules. Just to give you an idea, 1 megaton of TNT, 1 million tons of TNT, is about 4 times 10 to the 15 joules. Okay, so 1 kilogram converted to pure energy would be, more than, or about 20 times 20 megatons of TNT. Okay, mass has a lot of energy contained in it. Now, of course, it's not that easy to get that energy out. You can't just throw something in a furnace and like, hey, E equals mc squared, get all this energy out. Okay, remember the mass defects we've seen up to this point have been very small. But even though they're small, because c squared is such a big number, we can get enormous amounts of energy out from that. Okay, now we started by talking about the mass defect of a nucleus, and then we talked about the mass defect of a nuclear reaction. Okay, so let's talk about where does that missing energy go in the case of a nucleus. Okay, why was there a mass defect inside the nucleus? Well, now we know about mass energy equivalence. Okay, now we know that mass can be turned into energy or vice versa. And in the case of the nucleus, it goes into what's called binding energy. Please take good notes on this slide. Definitions are important. Okay, this particular definition shows up all the time on IB exams where they ask you to write the definition word for word of binding energy. Okay, there's 2 ways to define binding energy. Okay, either you can say the energy required to pull apart a nucleus into its individual nucleons, or the energy released when nucleons come together to form a nucleus. If you're asked to define binding energy, please do not say it's the energy holding the nucleus together. That's not what the definition says. It is the energy required to pull apart a nucleus into its individual nucleons. In other words, if I take my helium-4 nucleus and I reach inside and I take out those 2 protons and I take out the 2 neutrons and separate them, the amount of energy it took me to do that is defined as the binding energy for that atom. Okay. Notice that the term binding energy only applies to a single nucleus, not to a nuclear reaction. Okay, so when we talked about the mass defect for a nucleus, and that energy goes to this thing called binding energy. Okay, the mass defect of a nuclear reaction does not go to what's called binding energy, or I guess you could say it does, but we'll talk about that momentarily. Okay, so here you can just see kind of like a visual representation of what we talked about. If you were to take a nucleus and add energy to pull apart the pieces into its individual constituents, however much energy that took to do, that amount of energy is called the binding energy. Okay. Now, just to do a quick example, okay, take a look at example 1. Example 1 says calculate the mass defect of an oxygen-17 nucleus which has a mass of, I'm not going to read that number out loud. Okay, so oxygen-17, I happen to know oxygen has an atomic number of 8, but if you didn't know that, you would be given that on the IB exam question. And so oxygen-17 is made of 8 protons and, 9 neutrons. So to find the mass defect first, we want to find the mass of the 8 protons. So I have the mass of, let's say, 8 protons. Each proton has a mass of 1.007276. Remember earlier when I told you to write those numbers down, this is why. Plus the mass of 9 neutrons, that's 1.008. Let's see. As I record this, I do want to remind you, and I've said this before, I do want to remind you once again, please make sure that you don't round until the very end of the problem. Okay, so 1.008, say 665. Okay, this right here in brackets, that is the mass of the nucleons, the constituent particles, and now we need to subtract the mass of the nucleus, which is given in the problem. You would always be given that because there's no way for you to just know that. That's determined experimentally. So the mass defect here is going to be equal to this very small number. Now make sure you take very, very good notes over what I'm about to talk to you about, okay? Because this is important. I'm just typing this number into my calculator right now. Don't be surprised if you see a very small number for the mass defect. I get 0.1599415. Okay, so that's a very small mass defect. Here is something crucial. Okay, take good notes over the next few minutes so that you understand this. When you're calculating with mass energy equivalence, when you're using the equation E equals mc squared, E equals mc squared, remember that there's 3 units of mass. Okay, you have, not mean to erase that. Okay, that's fine. Mass defect. I did not mean to erase that, that's fine. I'm just going to write down the answer again. Remember that there's 3 units of mass. Okay, you have the kilogram, you have U, and you have MeV per c squared. Okay, those are the 3 units of mass we talked about. The equation is always the same. E equals mc squared. But there's different ways you can plug into the equation. I will tell you right now that if you're given the mass in U and you want to find energy, you must convert to one of the other units of mass. Okay, the reason for that is there's 2 units of energy you're going to see. There's MeV, that's mega electron volts, and there's joules. Okay, joules goes with kilograms. Those are both SI units. MeV per c squared, which is a unit of mass, goes with MeV, which is a unit of energy. Okay, if you're given the mass in U, you have to go to one of these other 2 units first. Okay, that's where you would convert using the conversion factors given to you in the data booklet. Okay, now once you have those other units of mass, how do you get energy? Well, that's where E equals mc squared comes in. Alright, so let's find this binding energy in joules first. Okay, so let's say I have the mass defect in U, and I need to convert that to kilograms if I want the binding energy in joules. Okay, so like any unit conversion, you start with what you're given. And the conversion factor that would be given to you in the data booklet is 1U is 1.661 times 10 to the negative 27 kilograms. Okay, 1.661 times 10 to the negative 27 kilograms. That conversion factor, again, is given to you. It's in the SI data booklet with all the other constants. Okay, so that's not a number you have to just remember or anything. So I'm going to take my mass defect, I'm going to multiply to convert it to kilograms, and once I have it in kilograms, I have 2.6566 28315 times 10 to the negative 28 kilograms. Once I have the mass, I can just use E equals mc squared, plug in, and I'm good. So I take this number right here, this really small number, and I multiply by c squared. Okay, so I plug in that mass times 3 times 10 to the power 8 squared. So remember, c is 3 times 10 to the power 8 meters per second. Okay, now I'm not going to write that out just to save room. Okay, but you can easily do that calculation on your own. And what you should get for the binding energy is 2.39 times 10 to the negative 11 joules. For binding energy, I write EB for binding energy. Okay, notice that's a very small amount of energy, but that's what it should be. So hopefully that's what you got. Please pause it there if you need to look over that some more, because I'm going to erase some of this stuff on the screen. Okay, that is the binding energy in joules. Now, what if we want the binding energy in MeV? MeV? Okay, well, if we want the energy in MeV, then we need to convert the mass to MeV per c squared. Now, if you're asking yourself, how do you know which one to do? Well, usually in the problem, it'll tell you what unit for the energy to be in. Okay, so that's normally given to you in the question. It'll say like find the energy in joules or find the energy in MeV per c squared. It's very typical to give you the masses in U and then force you to convert one way or the other. Because there's 3 units of mass and only 2 units of energy. So what I'm going to do now is I'm going to convert my mass defect to MeV per c squared. And again, the conversion factor is given to you. Okay, that is 1U is 931.5 MeV per c squared. Okay, don't forget how you say it. The negative exponent means it's per because you're dividing. Okay, so I'm going to do 0.1599415 times 931.5, and I get a mass defect of 148.9855073 MeV per c squared. And remember, that is my mass. Okay, even though it has a weird looking unit, that is mass. Okay, so if I want to plug in E equals mc squared, this whole thing is my m. Now, at this point, you might be asking yourself, why is this a unit of mass again? MeV per c squared. Why is it per c squared? Here's the beauty of this unit. Watch this. If this whole thing is mass, to turn this into energy, all I have to do is multiply by c squared. But take a look at this. If I multiply c squared, c to the power 2, times c to the power negative 2, those two units cancel out. And what are you left with? You're left with units of MeV, which are units of energy, which is exactly what we wanted. And now, since I'm at the end of the problem, I can finally round. The binding energy in MeV is 148.99 MeV. And that is the answer to the question, finding the binding energy of oxygen 17 in MeV. We found it in joules before. Okay, notice that this unit of mass has the convenience of not actually having to plug in a value for c, because the c squared cancels out in the equation. So that means if you get the mass in MeV per c squared, the value for the actual energy is going to be the exact same number. Okay, it's just going to be an MeV instead of MeV per c squared. MeV per c squared is a unit of mass, MeV is a unit of energy. Okay, so that is example 1. And I know there was a lot on there, so please feel free to go back and watch that video if you need to. Definitely take good notes, add things to your notes, ask questions if you have questions. Pause it there if you need to erase anything as I go to the next slide. Okay. Now, we are going to skip this one for now. I'm not going to work through it just in the interest of time, because I do want to end this video, but see if you can figure this out on your own. Okay, you should be able to do this calculation on your own using the masses of the protons and neutrons given to you, since those are constants. Okay, so you should be able to find the mass defect and then use the mass defect to find the binding energy in joules for copper-63. Okay, so pause it there. It might take you a few minutes, but go ahead and work through example 2 on your own. See if you can do that calculation. Okay, so what answer did you get for example 2? And I will tell you the answer I got, just so you can check yourself, is approximately 8.85 times 10 to the negative 11 joules. And so if you got that, then I think you probably have a good idea of how to find binding energy for a nucleus. If you did not get that, then please feel free to reach out to me and ask questions as needed. Okay, so we're going to stop the video here. Please let me know if you have any questions, and as always, I will see you guys in the next video.